Hello everyone. I'm a graduate student at the University of Rochester. I work with Professor Pengfei Huo on investigating new chemical reactivities that are induced by quantum mechanical effects. One example is, of course, the polaritonic photochemistry. The polaritonic photochemistry has emerged as an effective tool to modify chemical reactivities beyond the traditional paradigms of photochemistry. These are some of the recent examples. Forgive me if I haven't mentioned your work. Inspired by these works and some other works, we investigate the prospects of tuning electron transfer through the cavity QED process. Let's consider the non-relativistic Pauli-Fritz Hamiltonian that describes a molecular system coupled to a quantized radiation field. The first part of this Hamiltonian describes a molecular system. The second part describes the quantized radiation field. The third part describes the light-matter interaction that also includes the dipole self-energy term. The last part describes a dissipative environment which only fluctuates the nuclear degrees of freedom and doesn't have a state-dependent contribution. Now, the molecular system that we are considering here contains a colloidal nanocrystal and a molecular acceptor. The photo-induced charge transfer process that occurs between these two molecules can be described by these three states. One is the ground state, an excited donor state, that is a bright state, and a dark acceptor state. Now the electronic part of the Hamiltonian looks like this, where we have only considered the diabatic coupling between the donor and the acceptor state, which is responsible for the charge transfer process. The dipole moment operator in this basis looks like this, where we have not considered any permanent dipole as an approximation. And note, there is no transition dipole between the ground and the acceptor state as expected, because acceptor state is a dark state. The corresponding dipole self-energy term looks like this. And note, this term is no longer a state independent quantities as opposed to a two-level system. So this term cannot be just ignored as a constant quantity. Now, if we look into the light matter hybrid system, we have this rest state like G0 and D0, which just means the molecule in the ground state with 0 photons in the cavity, and then there is excitation to the nanocrystal part that and no photon in the cavity, that is D0. And of course, we also have the A0, which is the excitation localized on the acceptor molecule. And then we can also have states like the G1 state, which just means the molecule in the ground state with 1 photon in the cavity, which can be hybridized with the optically bright donor 0 state to give these polaritonic states. Now these polaritonic states, defined as plus and minus here, has different driving force as well as the diabatic coupling. So therefore the electron transfer will be significantly different to that of the bare molecular system. Now the challenge is that we have to find out the eigenspectrum accurately for this plus and minus state. To do this, we look into the subspace spanned by the donor and the ground state, and we define a polaritonic Hamiltonian that looks like this. Okay, and if we look into this polaritonic Hamiltonian, this is exactly a two-level system coupled to a quantized radiation field described by the Pauli-Fritz Hamiltonian. Now, there are different levels of approximation. We could use the Rabi Hamiltonian, in which you ignore the dipole self-energy term, and then further you can ignore the rotating wave terms and get the Janus-Cummings Hamiltonian. Here we assess the accuracy of these different levels of approximation in this charge transfer process as well. There exists analytical solutions for the Pauli-Fritz Hamiltonian, but they're very difficult to use because they're just solutions of some transcendental equations. So instead, what we do is that we take a rotating wave approximation first that allows us to obtain analytical expressions, and then group everything else, that is the counter-rotating terms, as a perturbative correction, which we add then back through second-order perturbation theory. By doing this, we get an approximate solution that works good enough for the range of parameters used in this work. Now, using this conceptually simple method, we obtain the eigenspectrum. In the analytical expression obtained here, we see that the first two terms just comes because of the JC Hamiltonian. Then the additional term, these ones, are just the contribution of the H dash that is computed through the second order perturbation theory, and which is just the counter-rotating term contribution. And the last one is the dipole self-energy. Now, in the resonance condition, roughly we can show that these contributions are half of the dipole self-energy. And we know that the counter rotating terms are important in the ultra strong coupling region. So therefore, the dipole self energy has to be also important, and this relative cancellation has to be included. So we see this by just performing a numerical calculation. This line represents the boundary between the strong coupling region and the ultra strong coupling region. Now you can see that we start with the exact, you ignore the dipole self energy, you obtain the Rabi and then do a rotating wave and then obtain the JC. However, exact is much closer to the JC than it is closer to Rabi. It is just because the cancellation of the dipole self energy and the rotating wave approximation makes the JC come closer to the exact, and Rabi overestimates the negative impact of the counter rotating terms. So that's why Rabi would be the worst one among these three. And then, of course, when we add this term through perturbation theory, you can see in this range works quite well. But obviously, this breaks down if you go further. We also use a quantum dynamics method in this work that is called PLDM, which we have recently shown to be very good in simulating quantum dynamics even in molecular systems. And we use this to compare our analytical expression obtained with the Marcus type expression. If we couple the molecular system to a quantized radiation field, we have these polaritonic states that are color coded with respect to the coupling strength. As you can see, because of the overall positive contribution from the dipole self energy and the rotating wave terms, the splitting is gradually increased for the plus state, but it is gradually suppressed for the negative state. And this makes a difference if I compare with the JC model, which always predicts an equal splitting of the plus and the minus state. So this gives an experimental way to see, to observe the effect of the dipole self energy as well as this Blog-Shaver shift that is coming from this counter rotating terms. Now, photoexciting the system to the minus state or the plus state and then changing the coupling strength would change the overall charge transfer process. And that's what we see. Here, I have plotted the acceptor population with respect to time at different coupling strengths. And as you can see, in a no coupling scenario where there is virtually any population in the acceptor state, there is significant amount of population if I increase the coupling strength. This can also be seen if I plot the rate constant as a function of the coupling strength. You can see the rate increases even if I compute with Pauli-Fritz or Janus-Cummings. It increases and then falls off. This is just because the system goes to an inverted type of regime. This can be called as an inverted regime that is induced by the light. Now, at higher coupling strength, the JC Hamiltonian and the Pauli-Fritz Hamiltonian predicts different results. This is because with higher coupling, the contribution of the dipole self energy and the counter rotating terms becomes important. So therefore, they have to be included. Now, instead of changing the coupling strength, the frequency instead can be changed to tune the electron transfer reaction. For example, here, we make a off resonance G1 instead of a resonant one in the last case. We keep G1 as close as possible to the barrierless regime. By doing this, we have a plus state that is near the barrierless regime. As a result, the driving force that is in the exponent enhances the reactivity, but at the cost of a lesser diabatic coupling. However, because the enhancement in the exponent is much bigger than the suppression in the diabatic coupling, this leads to an overall enhancement of the electron transfer rate. We see this by plotting again the acceptor population through time. Here, I'm changing the detuning frequency or the light frequency while keeping the light matter coupling constant. And as a result, by just changing the frequency, we have induced significant acceptor population through time. This is the rate at a particular light matter coupling, but changing the detuning frequency. You can see that this leads to an enhancement of the rate till a certain frequency. Then obviously, as the system goes beyond the inverted regime, the rate eventually decreases. In conclusion, we demonstrated that the charge transfer process between an optically bright an optically dark acceptor state, can be significantly enhanced or suppressed, and the dipole self energy as well as the counter rotating term play an important role, especially in the ultra strong coupling regime, and both have to be included in order to obtain a correct rate constant. This work complements the previous works done by other groups. So finally, I thank our funding agency as well as University of Rochester and my advisor Pengfei Huo, Todd Cross, and my colleagues. And finally, thank you for listening.